Okay, so you guys probably just finished watching Mr. Huffaker's video where he explains distance and displacement. And if you guys are like me last year, you guys were probably slightly confused by these concepts because they're very new concepts, especially if you're like me and you haven't taken physics when you learn this stuff. So I kind of want to talk about how the fundamental theorem of calculus relates to this displacement and total distance traveled concepts. So as we learned in 6.2, the fundamental theorem of calculus says that the integral from a to b of lowercase f of x dx equals uppercase f of b minus uppercase f of a, where f is the antiderivative for lowercase f. So let's look at this graphically. If we have this graph of an uppercase f and it is 2x, we're just going to have this linear line. And let's say that we go for 3 seconds or 3 x's. We're going to have this graph that has a slope of 2. And this makes sense. We've seen this linear graph 1,000 times. Just like this. Now, what is the derivative of 2x? Obviously, it's 2. So now we have f prime of x, or aka lowercase f of x, which we learned in the fundamental theorem of calculus that uppercase f of x is an antiderivative for lowercase f. So therefore, lowercase f of x is a derivative for uppercase f of x. So let's look at this graph here. We have the derivative of this uppercase f of x pictured here in this lowercase f of x. So it's just 2. And as you can see, we're going for 3 x's. And if we want to calculate the integral of this, we're just going to, as you guys know, calculate the area under this curve here. So it's just a rectangle, 3 times 2. The integral from 0 to 3 of f of x simply equals 6. And now we can really think of this using the fundamental theorem, that the integral from 0 to 3 of lowercase f of x is equaling the change in this uppercase f of x from 0 to 3. That is why the integral of lowercase f of x from a certain time to a certain time equals the change in its antiderivative, uppercase f, in that certain time period. And as we can see here, the integral of lowercase f of x from 0 to 3 is equal to 6 using the area under the curve. But the change in uppercase f of 3, obviously equals 6, and f of 0 equals 0. 6 minus 0 is also 6. So that just kind of proves that the fundamental theorem of calculus works. So the conclusion that we can draw here is that if we have the derivative of a function, which we did here, we can use that derivative to calculate the change of the function using the fundamental theorem. So basically, if we have a derivative, we can use the fundamental theorem to calculate the change in the function. Now let's look at that with displacement. So, displacement is the change in position, also known as how far you are from where you started, as we saw when Mr. Huff masterfully explained his polling example from when he went to the poll station and then came right back to his desk, so his displacement was 0 because there was no change from where he started. So, displacement, as we learned in 6.4, is from an initial time to an ending time, the integral of velocity. So, basically what we learned in the fundamental theorem, this is the same kind of setup, an initial to an end point. This is just v of t, this was lowercase f of x. So, displacement in reality is just this final x minus its initial x. So if we set it up like this as displacement, which we defined here, the integral from time 0 to time 1 of velocity equals x of t final minus x of t initial, which I am showing here. these will equal each other, which makes sense. And that looks awfully similar to this fundamental theorem of calculus that you guys learned a few days ago. And this makes sense because position is an antiderivative of v of t, velocity. So this is why displacement is equal from initial time to final time, the integral of v of t. That is why this all makes sense. So basically, with the fundamental theorem of calculus, it's saying that if we have the derivative of a function, we can use that derivative to calculate the change of the function using the fundamental theorem. So if you have the derivative of the function, you can use that derivative to calculate the change in the function using the fundamental theorem. That is exactly like it is with displacement. We are using the derivative of position, which is velocity, to calculate the change in position, otherwise known as displacement.